Hello everyone. So here's just a quick video to introduce you to a very simple network, artificial neural network, and to go over some of the Python programs that we've been talking about. Last week you did a tutorial by Dr. Andy Thomas. It was an introduction to neural networks for beginners. And this week what we're doing is trying to go and do some programs to explore deeper how these things work. And so we're going to be prodding and kicking and doing everything we else can to this simple network that's shown here, and in the process hopefully learn a little bit more about how these things work. Okay, now the one that was in the tutorial is a little different than this one, and the main difference here is this extra output node that I added, and I modified his sample programs to include this extra node here. And I've labeled my inputs as Q1, Q2, Q3. So this is some number that we're putting in, this is some other number, and this is some other number. And then these are output nodes that have some value between 0 and 1 for here, and some value between 0 and 1 for here. Okay, now just to kind of look at the structure here, you'll see you've got an input layer, which in this case has 3 input nodes. We have a hidden layer, which has 3 nodes. Now they call it hidden because it's in between these two, but obviously we can see them. And then we've got 2 nodes for the output layer, and I'm calling this output node 1 and output node 2. Notice also that I have some W things here. These are weightings for the path between different nodes here. And so for example here, when I say W11, what this 1 here refers to is that it's to the node 1, and this one here signifies that it's from this node 1 over here. So this is where you're going to, and this is where you came from. And so just to give you another example here, is this is node 3, so we're going to node 3, we're coming from node 1. We're going to node 3, we're coming from node 2. We're going to node 3, we're coming from node 3. Okay, so input, hidden, and output. Now what we talked about, or what you saw in the handout that you worked with last week, was that the way this works is you have some number or some value coming in here, some value coming in here, and some coming in here. And so I'm calling this Q1, Q2, and Q3. And this number, say this number is 2 or 3, coming in here is multiplied by W11, is multiplied and goes to here, and then this is multiplied by W21, and then this right here, the Q1 is multiplied by W31 and goes into here. Now you'll notice that there's 3 inputs coming into here. Well, these 3 inputs come in, plus there's a bias that's assigned to here, which I don't show in the diagram. There's a bias here and a bias here, which are signified by B1, B2, and B3. And then there's another bias over here, but what happens is this takes these 3 inputs, W11 times 1, W12 times Q2, and W13 times Q3, adds those together with the bias, and then it applies it to the sigmoid function that we saw in the tutorial. And then the output goes out on here. Now here we have another sets of weights. Now notice this one has 3 inputs, one from here, here, and here. In the same kind of nomenclature, this would be W1 from 1, W1 from 2, W1 from 3. Okay, and so this would be output node 1 and output node 2. Now the way that we should look at this is basically these are some inputs, like let's say that you're trying to identify a bird. Maybe there's a family of birds that you want to distinguish. This would be a classification problem. Okay, and say one here could be like the woodpecker, and right here could be like a blue jay. Okay, so over here we could have inputs like wingspan, maybe the color of the bird, what location of the country they're found, whatever. So we'd put some value, a numerical value here that would represent this, this, and this. And hopefully over here, this would give us a value that would basically a higher value for a woodpecker and a lower value maybe for a blue jay, or vice versa, depending on what it was. So what we would normally do is would say, like, we want, if it's a woodpecker over here, that we want a high value for this one because we're calling this the woodpecker output. If it's a blue jay, then we'd want a high value here. And by high, I'm talking about close to 1, and low would be closer to 0. So what we would want is, if you put all the characteristics of the woodpecker in here, then we'd want this value to be like a 1, or pretty close to 1, 0.6, 0.8, somewhere around there. And this would be really low, like 0 or 0.1 or 0.2. However, if we put in here the stuff for a blue jay, then we'd want this to be a low value, and this would be a high value, closer to 1, and this closer to 0. Now the interesting part is, what if you put something in here like a duck? You know, the question is what kind of readings would you get here? And that's what makes neural networks so interesting, is you train it to recognize certain things, like in this case a woodpecker and a blue jay, but what happens to a case where it's not been trained for? Okay, so anyway, that's kind of what we're doing, is we're going to be putting in Q values here to inputs, and we're going to be looking at the output nodes, and one of the programs we're actually going to go through and train each one of these weights, or come up with values for the weights that actually produce the correct output. So when you're programming these, really what you're doing is you're actually going in and determining or choosing the weights for each one of these, and for these, and the biases for each one of these, so that whatever your input is, you get the desired output over here. Okay, so you train it so that it recognizes a woodpecker, it recognizes a blue jay, and things that you haven't trained for, well, that's a big surprise. Sometimes it's not surprising, sometimes it's very surprising. Okay, so this is the basic thing that we've been doing last week, and we'll continue on this week. Okay, so let's look at some of the programs. Okay, so here's the Python idle shell, and let's pull up the first program. Okay, so this program here is the this is the one that we called A. Okay, so it's ANNA is the one that we're doing. This is in task 1. And so I've got lots and lots of comments, and like I say, this is essentially the program that we were working with from the tutorial, by Dr. Andy Thomas. But I went in and made a few changes here and there. The biggest part was right in here, where I went in and I've got 2 output nodes. Okay, now I'll let you go through and read through this, and you have these files so you can go through. Q1, Q2, and Q3, these are the inputs. So I have 1.5, 2, and 3, and there again, this is basically Q1, Q2, and 3 from there. Okay. And so here's our sigmoid function. Here's the actual feed forward. This is actually doing the calculations. And in this case here, for this program here, we're using the weights that were used in that example. It was on a page, let's see, what was that on? That was up to this was up to page 15. So pages 1 through 15, these are the weights and stuff they were using. Notice here that you have the W1 weights, okay, and here I'm saying like W11, 12, 13, so 0.2, 0.2, and then from 2 is 0.4s, and then from the 31s are 0.6s. So if we go back in here to this again, So everything coming into here is weighted by 0.2, this is 0.4, and this is weighted by 0.6. That's what the W's are for. Okay. And then what I have is I have the weights for between the hidden layer and the output layer, and you notice these are all 0.5 for all these. Okay. So these are all 0.5, 0.5, 0.5, 0.5, 0.5. And like I say, I added this extra node, and just to check it out to make sure that I didn't do anything wrong, essentially what I did was I made this output node have the same weight, so this is going to produce an identical output for that initially for this first program. Later on I'll change the weights here, or actually calculate different weights to produce different outputs here. Okay, and when you're training, we're talking a lot about training, especially in the next program. Essentially what you're doing is you apply a certain input and then you want a certain output. Okay, and so that certain output, this would be like R1 and this would be R2, and so when you don't get the output you want, then you basically end up with an error. So your output node minus the value that you wanted is an error, and that can be used to actually go in and optimize or determine these weights, the weights here and the weights here, and the biases to actually produce the desired output for here and the desired output for there. But in this case here, this program, these are all 0.5, these are all 0.5, this is going to produce the same thing as that. These are 0.2s, these are 0.4s, and these are 0.6s. Okay, so the 0.2s, 4s, and 6s. Okay, so there's the weights here for the output for the two, hidden node, output node 1, output node 2. Now here's the biases that we're using here, and like I say, these weights and biases are the ones that are in the example, and I use this just to verify that I was getting the same results that they did in the tutorial. So you'll be changing some of this. And then here is for the middle to output layer, the biases 0.2, 0.2, and 0.8. So the biases for the middle node or the hidden node are all 0.8, and then the biases for the two output nodes, B2 and 3, are 0.2. And then here all I do is pretty much like you did in this program, is I went in and take the weight 1, weight 2, and weight 3 and put them together in a list here. Do the same thing for the biases, and then the same thing for the inputs, Q1, Q2, 3. Okay, so the inputs, the biases, and also the output weights. Okay. Okay, and notice here that I've got B2, B2. I could have said B3 here, but it doesn't really matter. I've got the same thing here, so why don't I just go ahead and correct that? Okay, there you go. So B3. All right, and then we've got the number of layers of 3. You got the input layer, the hidden layer, the input layer, the hidden layer, and then the output layer. So that's 3 layers. Okay, and so now what we're going to do is we're going to run results. Okay, let me bring this other one back up. Okay, a little bit of technical difficulties here. Okay, all right, come on, come on. All right, here we are. All right, so what we're going to do is we're going to run the program. So here what we're doing is we're calling the function matrix feed forward calculations, which is defined right here. Okay, so this is the definition here. And it's going to output a node 1 and node 2 to output. We're inputting the number of layers, the input values, x's, all the weights, for the input to hidden, and the weights for the hidden to output 1, and the weights from hidden to output 2, the biases for the hidden nodes, the bias for the output node 1, the bias for output node 3, and then the inputs. Okay? And like I say, all the weights and biases and everything are just like they were in the tutorial up to page 15. Okay, so all we have to do is go ahead and run it, and notice it's going to print the results out here. So let's go in with this value here, and we go to run module, and okay, let's save it, and there we go. Okay, so here I'm just printing out everything. Okay, so we got weights, I just printed that out, the biases and everything, and then what I did was I printed out the results of the run. And if you look in the tutorials, you'll see that this is exactly what the tutorial did. So this was a quick check on my programming to make sure that I didn't do anything dumb here, and hey, everything looks pretty good. So that's all this new program's doing, is basically just to go in and check that everything's okay as far as the functions input right and all that other stuff. Okay, so let's go back to here. So anyway, this is mainly one just to give you lots of comments and explain to you what's going on and everything. Some of this stuff we can talk about later, the dot mode and stuff. That's something you may not have been exposed to. Maybe have, maybe haven't. But anyway, this is the code, okay, for that. All right, now let's go and let's look at program number 2, which is essentially this is B, so this is ANNB program. Okay. Good. All right, so here what we're doing is similar to the other one, but what we're doing is we're allowing for some input. Okay, and the way you do input here, notice I've went in and I commented out the values that we started with, which were the values for the tutorial. And what I've done is I've said, okay, well, what we're going to do is we're going to input this as we run it. And so we'll input Q1, Q2, and Q3. And we're still going to keep the same weights that we had from the tutorial, so we haven't changed anything there. Okay, and so like I say, this is the same network or the same machine that we had in the tutorial and that I had from program number 1, which was ANNA. Okay, it's just that now we can input. So let's go ahead and let's run it. Save it first and run. All right, and so now what I've got is down here, if I can pull this up here a little bit, we've got some inputs here. All right, and so I'm going to put 2.0, enter, and I'm going to put 1.4, enter, and then I'm going to put 3.0, enter. And what did it give me? It gave me the same thing. Okay, well, that's not good. Control, oh wait, yep, 3519. Well, it's not the same, but look at the input here. The input was 2, 1, 4, and 3, and the input before was 1.5, 2, and 3. So it looks like having a 2 there instead of the 1.5 and a 1.4 from 2 really didn't produce much of a difference here. Okay, so anyway, I'll go back and check this to verify, but that's all you do. So let's go back and let's run this again, but this time let's go in and put some really different values in here. So let's go and run it. Okay, and let's put in a 1. Let's put in a 0.5, and let's put in 0.7 and see what happens. Okay, in this case here we end up with a different value. This is 0.810866649, whereas it was 0.835. Okay, so doesn't seem like a whole bunch, but anyway, that's the whole purpose of this program here, is to actually go in and just show you how to do input stuff. Okay, and so that's all I had to do, was something like this to do input. Okay, all right, let's go to the next program. Okay, now this is the first program where we're actually going in and doing some training. Okay, so let's go down here and pull this up. Come on. Okay, good. Microsoft Windows. All right, now let's look at this program. So this one is called ANN Trainer. Okay, and so far it looks the same here, but here's where we're getting a little bit differences here. Here what we're going to do is we're going to go through and actually figure out some values for the weights that hopefully will produce our desired output with a given input. Now for here, this is kind of a really silly one, because all we're doing is we're training it for one particular output. Okay, so let's see what we got. So we're initializing the weights, a 1 through 15, and then our inputs here are 1, 2, and 3 and out. And so this is the training data here. Let me just go ahead and put a comment here. So training set, data set 1. Okay, and this is the only one we got. So what we want is we want that if Q1, Q2, and Q3 are 1, 2, and 3, then we want R1, which is output data 1, to be 0.2, and we want R2, which is the second output, to be 0.6. Okay, so just bringing this photo back up, what we're doing is we're putting Q1, 2, and 3, so we're putting 1, 2, and 3, and then we want this, which would be R1, and this would be R2. We want those values to be 0.2 and 0.6. Okay, so 1, 2, and 3, if that's input, we want 0.2 for this, and we want 0.6 for that. Okay, so we need to determine what values for these weights, and these biases will give us that. Okay, now let's go in and let's look at the weights that we have. Down here, if we look at the weights, we're going in and we're using, we're going to determine these values and these values. But what we are doing is we're not going to play around with the biases. We're going to set all the biases to 0 here. Okay, so that's the only thing in this. Now, if we had a lot of time and really, really fast computers, then we could go in and do a search for the biases and stuff. Or if we used a sophisticated algorithm. But I chose not to use any calculus in here because you guys have not had calculus yet. And so I think that the way I'm doing here, even though it's not a practical way to do this, it'll give you some idea of how you go through and search and find the correct weights to actually go in and make the program work. Okay, so first off, let's look at t. Okay, so this is in an arrange type function. This in NumPy. And what this says is basically we go from -1 to 1 in increments of 0.2. So we go -1, minus 0.8, minus 0.6, minus 0.4, minus 0.2, 0, plus 0.2, plus 0.4, so on and so on. Okay? And so for each one of these loops here, A1 is going to be, one of those values. Okay? So it'd be from -1 to +1 in increments of 0.2. It's going to systematically go in and scan all those, all these, all these, and these. And so as you can see, you've got how many points here? You got -1, minus 0.8, 0.6, 0.4, 0.2, 0, 0.2, 4, 6, 8, 1. So you got about 11 different values here, 11 or 10 values. So you got, say, 10 values here, 10 values here, 10 values here, 10 values here. So we're going through all the possible combinations, right? And so this would be 10 times 10 times 10 times 10 times 10, all the way down here, 10 to the 15th, right? 10 to the 15th. That's a very, very big number. And for a computer to go through this is like what's called an exhaustive search. Your computer is going to be exhausted, and it may take all night and may not even finish running then. Okay, so what we're going to do here, just to make life a little bit easier for here, we're going to basically go in and we're going to say, let's count from 0 to 1. Okay, and I'll need to go check and see, but I think this function here may just go from 0 to 0.2 to 0.4 to 0.6 to 0.8 and not do 1 unless I go in and put some special option here. So anyway, it's going to go through and do the values. So this will cut down on the number of values. And so what we're going to be doing is we're going to go into here and we're going to count the number of iterations. We initially set I equals to 0 up here, right here, right? And so every time we go through an iteration in this loop, we're going to increment I, okay? Now, here is going to be W1, okay? These are the arrays for the weights between the input node and the hid node. So here's for the top node, the middle node, and the bottom node. And then these are the weights between the hid node and output 1, the hidden node, and output 2. Okay? And so these are the values that we're going to try to optimize, right? And we're leaving the biases as they were in that, well, actually we set all the biases equal to 0. All right? So we go in and we sum all these up. Then what we do is we actually go in and call the program, all right? And by program, I mean this thing right here, okay? So this is what's going in and giving us the output, all right? So what we do is we feed in the weights here. The bias is all 0. The X is the actual values that we put in, the Q1, Q2, and Q3. So that's 1, 2, and 3. And the number of layers is 3. Okay? Now, when we go in and we do this is going to return output node 1 and output node 2. Now remember, this is output node 1 and output node 2. Okay? So what we'll do is we'll run this with these particular values, okay, of weights, and then we'll go in and look at the error, okay, and so we take output node 1 minus y of 0. Now y of 0 is the desired value that we want for this, okay. Now the desired value that we want for this is R1 is 0.2, and so this is for output node 1, and then the other one is 0.6. So looking at this, we want 0.2 for this, and we want 0.6 for this. This is R1, and this is R2. Okay, so what we'll do is we'll go in and we'll take the difference between what we've got with these weights, what we want, square it, and then add this same thing for output node minus y of 1. So this would be R2. And square it. So this is going to give us error. Okay. Now, what we want to do while we're searching for this is we want to find the values of weights that give us the smallest error. In other words, we want to find the set of weights which are A1 through A15, which produce an output that's closest to the output node 1 being 0.2 and the output node 2 being 0.6. And so the way we do that is we basically start out with a really, really large error. So m equals 1 to the plus 6, which is really large. So we go in and we say, if this error here is less than m, then we want to save it. So m will be equal to this error, and A1 through A15 will be equal to the values of these weights that we did in this iteration. Okay? And then here what I'm doing is I'm just basically going in and saving also out 1 equals this and out 2 equals that. And then what I'm doing is I'm printing this. Okay? Okay, so once we've gone in and we found the values, okay, those will be these values here, all the A's and this. Then what we want to do is we want to go in and run the program again with the desired input and verify that that produces something that's pretty close. And so here we have W1 equals A1, 2, 3, A4 through 6, A7 through 9, and then W2 is this, and W3 is that. So we put it back to here, we call the program again, and then we print the final results, node 1 and node 2. Okay? Now, this takes a long time. That's why I cut it down to really get a really accurate value here. You need to do much more than this. This is only checking the values 0, 0.2, 0.4, 0.6, 0.8 for each one of these values. Okay? So that's 0, 0.2, 0.4, 0.6, 0.8. So that's like 5 times 5. So that's 5 to the 15th, which is a lot fewer iterations than if we did the whole thing. So let's see how close we get to that. Let's go in and let's run it. I guess we probably need to save it first and run it. And it's going to keep running. It'll show you the iterations it's going. And what happens here is it's still running, okay? But what it does is when it gets a value where a new value that's better than the last one, okay, then it will stop and it'll show where it's at, okay? And then eventually it'll go through and hopefully it'll stop. I don't think I'm going to wait too long, but right now you notice that we've done 31,000 iterations, and here's the values that we're choosing. And notice that what we're getting is for out 2 we're getting 0.5, out 1's 0.5, out 2's 0.6, and really what we want is we want something close to 0.2 for this and something close to 0.6 for this. I think, is that right? 2 and 6? Yeah, 2 and 6, that's what we want. Okay, so it's still going through iterations. And what I said in the assignments was I wanted you to go at least, I think it was like 300,000 iterations before you stop. But it depends on your computer. I'm running this on my old computer and it's going much slower than my gaming computer did. So we'll see. We'll give it just a few more minutes here. And because I don't want to waste too much time on this video here, you're sitting waiting on some inputs, but it's still running. It just hasn't found a better thing. And notice, don't worry about these being 0. That's just the last time that it checked. That was the best case. When a new case comes up, some of these values will change, and hopefully these will change. Wow, did I just get a new value? Well, let's see. Whoa, it takes a long, long time. So that's why I say, once you get up to about 300,000, stop. Come on. Faster, faster, faster. Like I say, this is not the best way to find these. I just did this because I thought you guys would understand this better. Had you had some calculus, I would have used the calculus approach. But what we'll probably do maybe next week is I'll go in and show you how to search using genetic algorithm, which I think you guys will find to be a little bit more understanding and not as much calculus. Actually, very little. Okay, well, you know what? I think I'm going to go ahead. Well, there's one there. This is still 0.5, 0.6. Oh, there's another one. about 200,000. Well, 200,000. Now we want this to go to 4, and this one here, this to be about 0.6, or no, we want this to go to 0.2. There's 200,000, so just when I stop, it's probably going to do it again. But anyway, we're going to stop here. Now the way you can stop this is if you click inside here so that this is active, if you do Control-C, it'll stop. Okay, so if you get up around 300,000 or 400,000 and it still hasn't stopped, then basically you can do this depending on your computer. And then basically what you want to save is you want to save these values here. And notice these are the actual values of 0.2 for this, these. And here is my output, 0.599 and 0.5. You won't, a lot of times you'll get really close, but sometimes maybe not as close as you want. And it depends on how many points you evaluate and where. We're only looking at very few points. Okay? All right, so that's what this program's doing. Okay, now let's go to the last program. And this one here is the ANND. This is the one where we're training 2 sets of data. Okay, so up here is pretty much the same as the one we just did. Where it's different is we have 2 training sets. We've got a 1, 2, 3, and we want a 0.2 and a 6 like what we had on the other one. And then here what we have is an input of 2, 1, and 0.5, and in this case we want a 0.7 and a 3. Okay. Here's where I go in and combine them. And down here I'm doing the same thing, you know. Let's go in and do the same thing that we did on the last one here. Let's go in and let's change this to 0. And so here for each one of the t's now we're going to be checking the values 0, 0.2, 0.4, 0.6, 0.8 for each one of these. Okay, so every possible combination of those is going to be checked. So that's going to be what, 5 to the 15 different iterations. And then what we'll do is we'll basically go in and we'll do training set 1. So we'll go in and get the weights here. We'll go in and we'll do an output 1, 2, 1 and 1, 2. So this right here represents node 1. Case 1 or training set 1, node 1, training set 1, node 2, and this is training set 2, output 1, training set 2, output 2. Okay, so we go through and do this, and then we get an error. Okay, so y1 of 0, y1 of 0, the error, and then here y2 of 0. So this is just like we did before, except now we've got some other errors we're looking at. Okay, and then here if the error is less, you know, then we go in and save the results. And so here I'm printing out the whole thing for this one. So let's go ahead and let's run. Now while it's doing that, let's just look back at the image here again and notice that what we've got here is we got a set of values that we want to get a certain value output, and then we got and that's called a training data set. Then we have another training data set on the input here, and we have a different output. So what we're doing is we're going in and checking all possible cases, well, within the values we specified, for W's here and W's here, and we're setting the biases 0 for both of these layers. And so in the end what we'll have is we'll have some optimal value from that given set that we searched. And we didn't search the whole set. We searched for values of 0, 0.2, 0.4, 0.6, and 0.8. So out of that set, or that domain, we're trying to find the best combination of values to give us what we want for the outputs given a certain input. Okay, and notice we're only training it for 2 data sets. Okay, so where are we at now? We're at, well, iteration 1 gave us not very good. Let's see what we get for another iteration. Well, obviously the first iteration is going to be better than the big number we had before. Okay, this is taking a while. Okay, let's get one more iteration. All right, come on, you can do it. One more iteration. Come on, let's do it. And like I say, this one's going to take a little bit longer because we're doing twice as many calculations for each one of these cases. Let me see if there's something on here we can talk about. We've already talked about all this here. Okay, just one more. Okay, like I say, don't worry, it's still running. It's just it's only printing out stuff when we have a change, because it's in this loop, right? It's running all these for loops and doing all these calculations for each iteration, each value of the A's. And then when the error is less than what it was before, then we actually go in and get a new printout. And in this case here, iteration 1, we had an error of 0.18. So before we print anything else out, unless we end, it's going to have an error less than 0.18. Okay, well, I'm going to stop right here. This video is dragging on a little bit longer. So anyway, go over this video, go over the instructions that we did in Blackboard, and if you have problems, let me know. Catch you later.